Okay, so now that we know all the parts that go into making up a spectrophotometer, let's talk a little bit about how we might put these parts together and how this has been done historically. Again, there are going to be three types of instruments that I'm going to tell you about: single beam instruments, double beam instruments. I'll also tell you again about the photodiode array instrument, which is sort of taking things over these days. Okay, now the simplest design is called the single beam spectrophotometer. The name suggests it's only got one beam, and that's what makes it very, very simple. Let's take a look at how you would build one of these, okay? Over on the far left, it's hard to read, but that's the source. It's a light bulb. In one of these, you'd probably have at least a tungsten lamp for use in the visible region. You might also add a deuterium lamp so that you have a UV light. And they usually take the light from both of these lamps, combine them, and then pass the light through our monochromator. The monochromator is the next component. It's usually placed right after the source to spectrally select. Then you have your sample. Sample, again, is contained within a cuvette. It's a sample holder for liquid samples. Now notice that there are two square cuvettes here. One they call the reference cell, and the other is the sample cell. Generally speaking, the way that the single beam spectrophotometers work is the user needs to manually change the reference cell and the sample cell. Okay, now obviously the sample cell is going to contain the sample that you want to make a measurement of. But to get a transmittance reading, you also need two other points. You need a 0% transmittance where all the light is blocked, and you need 100% transmittance so that you can span the full range. Your sample will be somewhere between these two extremes. So the way that the single beam spectrophotometer achieves these 2 points is for the 0%. There's a little beam block. It's sometimes referred to as an occluder inside the device. And basically, if you don't have any cuvette in the device, this beam block basically comes down into the beam's path and blocks the light from reaching the detector. So the sensor is basically able to use the signal that results when all the light's being blocked as the 0% transmittance, okay? So it can set to 0. Now the 100%, or the blank, has to be set manually. And the way that the user does that is basically takes the reference cell, which is a separate sample. Now that usually contains the solvent that the sample is dispersed in and the matrix for the sample, basically everything else except what you're trying to measure the light absorption of. You can place that solution in an identical cuvette and set the blank or 100% T of that reference solution at the wavelength of interest. Then what you do is you take that blank out of the device, insert your sample into the device, and then make your transmittance measurement. Okay. Now, after the sample cell is a photodetector, that's our transducer, that takes our light intensity, converts it into an electrical signal that we can then amplify and read out. So these are the parts for a single beam instrument. And the thing that really makes this, how you can identify this, identifying, is this idea that to use it, you have to take your reference cell, place that in, set the 100% T, and then remove the reference cell to actually measure your sample. Now, the major advantages of the single beam design is it's extremely inexpensive, relatively simple to understand, and straightforward to pull off. But there are some disadvantages to the single beam instrument. The main disadvantage is that source intensity fluctuations can't be eliminated. This is a big disadvantage to single beam instruments. If that light bulb gets brighter or dimmer during the course of your experiment, that is from the 0 to the 100% T onwards to the sample, at any point during that experiment, if the source intensity brightness changes, you're in a bit of trouble, okay? Because you cannot account for that change in the single beam instrument. Now, there's another type of spectrophotometer that I want to tell you about. It's called the dual beam design. Let's take a look at the dual beam design real fast. Now, first off, it can be dual beam in space or dual beam in time. And as we explain it, I'll basically explain what we mean by that, okay? But what's important to know in the dual beam instrument, as the name suggests, going to be two beams. Two beams. And because of that, we're going to direct the light from these two beams through two different cells. One for the sample and one for the reference or the blank. So those are going to be our two cells, okay? So one's going to be for the sample and the other one's going to be for our blank. I'll explain where we place them here in a second once we start looking at the figures. Now, this is a dual beam approach. There are two beams and there's going to be two cuvettes. When we use these cuvettes, we want them to be matched. If we use more than one detector, we want them to be matched as well, meaning that they have been manufactured to be as identical as humanly possible. So in one of the last videos, I mentioned that oftentimes high-grade cuvettes are made out of quartz for use in the ultraviolet, and usually when you buy those, you have to buy a matched pair. Now we can start to see why you might buy your cuvettes as a matched pair. Basically manufactured at the same time with the same people involved, the same optical glass that's being used, and they produce two cuvettes that are essentially a matched pair, which are as identical as possible to one another. The reason why we do that is because if you're going to use a dual beam or double beam spectrophotometer, you need two cuvettes, and you don't want one to be different than the other. You don't want them to have different transmissions. That would kind of bias your experiment or cause some systematic error. So we want to use a matched pair of cuvettes that are as identical as humanly possible, okay? All right, now let's look at some of these diagrams over here and see if we can make sense of these dual beam approaches. The first one I'm going to describe is up here at the top. The one at the top is going to be dual beam in space. So over here, we've got our source. Again, that's going to be either our tungsten lamp alone for the visible, but if you got one of these instruments, you're probably going to use a tungsten lamp plus a deuterium lamp. And you're going to combine the light so that you've got photons all throughout the UV into the visible and throughout the visible region of the spectrum. So if you combine the light from those lamps, which is commonly done, you've got light for the entire UV vis region. We're going to take that light and again pass it through our monochromator. Get only the wavelength band that we want. The light that comes out is going to be passed to a beam splitter. As the name suggests, it's going to split the beam. Now, for the purposes of our discussion here, I'm going to say that that split is 50-50. Actually, it doesn't have to be, but this is easier to explain, I guess, if it is. Okay, so 50% goes that way, 50% of the beam goes this way. So we've now generated our two beams for the dual beam approach, haven't we? I use a mirror here and a mirror here to redirect the beam through a sample cell and a reference cell. The reference is up at the top. That's basically going to be our blank or our sample solvent and matrix, but no light absorber. And then the sample with the substance which absorbs will be down here in the bottom. So what's going to happen? Well, I'm going to have these two matched cuvettes as similar as possible, okay? So light will pass through both of those samples. But of course, if this bottom sample is the material that absorbs light, the output intensity down here will probably be a little bit lower just because some of that light has been absorbed by the light absorber. So I'm going to take two photodetectors. These are transducers, whatever type I'm using. Put one here, put one here. Each one monitors the light intensity on their separate channel. And then I can use an electronic circuit called a difference amplifier and a ratio, or really, that ratios the, let's see, let me erase this. Looks like there's already terms for it, P and P0. Okay, so this difference amplifier can ratio P to P0, which is the irradiance that passes through either one of these sample cells. And of course, that's then equal to my transmittance. Multiply that by 100, I got a percent transmittance. That can then be shown here at the readout, okay? So this dual beam in space approach basically just splits our light beam into two separate beams, and then you make your sample reading and your reference or your blank 100% T reading at exactly the same time, okay? Now, what advantages does this have? It seems much more complicated than single beam. Well, the major advantage of the dual beam approach, this is kind of why it was invented, is it eliminates source intensity drift. Remember earlier with the single beam, I said, oh, you know what? If that light bulb gets dimmer or brighter over the course of your experiment from the 0 point to the 100 to your sample, that's error, right? And indeed it would be. But in this design, I'm taking the light from my source, and since I split it in two, I can make my sample measurement and my reference measurement at exactly the same time. So if my light source gets brighter, well, both of these signals will get proportionally brighter. If my light source gets dimmer, both of these signals will get proportionally dimmer. And the beauty of this is that the ratio will always reflect the true transmittance of the sample. So it's oftentimes said that this dual beam approaches more or less account for source intensity drift, and it corrects for it. So it's a better design for a spectrometer. Of course, it's more expensive as well, but considered a better design. All right, and the second one down here at the bottom is also a dual beam. This is a dual beam in time. Using our spectroscopic source, again, that's going to be a tungsten lamp. Plus a deuterium lamp, so that we can get light throughout the UV with the deuterium lamp, and a tungsten lamp provides us with our visible. We'll take that past the light through a monochromator to spectrally select. And now what we do is the output beam is directed towards what's called a sector mirror. And the sector mirror would look like this. Basically what it is it's this little device. Half of it's mirrored and half of it's transparent. And more or less it's attached to a motor that basically rotates it around in a circle constantly at a certain rate, a certain number of revolutions per minute, okay? So if we look very closely at this sector mirror down here at the bottom, that's actually key to understand how this works, okay? This darkened region on the top and the bottom is basically our mirrored surface. So if the light hits that, it will reflect off. But the other regions, which are not darkened, are said to be just transparent, like a window where light will just pass straight through it, okay? So what I want you to think, if we do make a motor right here and basically spin that, what's going to happen? Okay. Well, if the light comes in and hits just at the right moment, right, to hit the mirror, so if the mirror is in the beam's path, it'll be reflected up. But if I wait a fraction of a second longer, because remember, this thing spins, right? If I wait a fraction of a second longer, the light beam might hit the transparent region. And in that case, it would just pass straight through, right? And this is going to happen over and over again. As the mirrored region moves into the beam path, reflection. As the transparent region moves into the beam path, straight through transmitted, okay? Now what are we going to do after that? Well, we're going to have two cells. Up top is our blank or our reference cell. That's going to set our 100% transmittance. This is typical. And then down here at the bottom is our sample, which contains our light absorbing substance. So when the mirror is present, the light will come through the reference cell. It'll pass through the reference cell and then hit our photodetector, recording a signal. On the other half cycle, when the transparent region is in the beam path, the light will be directed to the sample off a mirror and to the same photodetector. Now, what the electronics of this device does, if you look at our signal output over time, let's think about that. So this is time, and this is signal at the detector, okay? Let's think about what happens here. So during the period where the mirrored surface is in the beam block, or in the beam's path, excuse me, okay? what's going to happen is you're going to get the reflection through the reference cell. And your signal at the detector will be a certain level. Then that mirror rotates a quarter turn. And all of a sudden, when it does that, the transparent region's in the beam path. So light goes straight through, doesn't it? Now it's going through the sample. So I would expect the signal to be a little bit lower. And the reason why is because the sample contains some sort of light absorbing substance, doesn't it? So it's going to absorb a portion of the light at this particular wavelength. Then that sector mirror will rotate another quarter turn. And what happens? Well, now we're back to the blank measurement again, right? And then another quarter turn, okay. Back to the sample. If I can write it on the thing there, okay. So you can see that this happens over and over and over again. Blank sample, blank sample. And you know what? If I even put a beam block in here, I could measure my 0% as well. Which of course would be down here, 0%. It's like a dark signal, right? So with my 0%, with my blank setting my 100%, I can measure the percent transmittance from my sample, which is what I want. So this is the dual beam and time approach, because over time, I basically alternate back and forth between my reference measurement and my true sample measurement. All right. Now the advantage of it is it only uses one photo detector. So a little bit cheaper, you don't have to buy two. It's also sometimes hard to match the photo detectors perfectly, but this one just uses one. So you know its sensitivity to light is the same for the reference cell as it is the sample, which is actually a really nice thing. And you say, oh, well, how can this account for source intensity fluctuations? Generally, we say it does account for source intensity fluctuations. And the reason why is because this mirror spins reasonably quickly, reasonably fast, okay? You know, many times per second. And because of that, there's not much time difference between when we make our sample and our reference measurement. So you know, this design really does correct for longer term source intensity fluctuations, okay? Okay, so that is our two historical types of spectrophotometers. Now, the next thing I think I would like to do with you here, if I can, I'm hopeful that this works out, okay, is to tell you a little bit more, just remind you more than anything about this other type of spectrophotometer. I hope that this works, which is called the photodiode array spectrophotometer. And sure enough, it's going to cause all sorts of trouble, right? Let's see, now I don't see the diagram. Yeah, figures, okay. Well, let me go. No, I don't want to sign up. Let me just do a search real quick. Yeah, figures, huh? Okay. This is always more difficult than you think it's going to be when you're working on the Zoom to get something good. Let me just go to Google here. All right, we'll do this a different way. All right, let me see if I can show you. These are all photodiode arrays. I kind of searched before class to find a good website for you. And this is the one I was going to show you, I believe. But the website's not so user-friendly. It makes you want to sign up for subscriptions and such, and I don't want to do that. So I'm just going to have to go through it here in the Google. Okay, so what you're seeing is the basic idea behind a photodiode array spectrophotometer. I told you about this at the end of class last time, okay? You got your spectroscopic source down in the bottom right corner. That's your light bulb producing your UV and visible light. Again, that would typically be a deuterium lamp plus a tungsten lamp. You use those two lamps. So again, you get wavelengths throughout the entire UV visible region. You pass that light through a sample, all of it, all the different wavelengths. It comes out the other side, then goes into an entrance slit where you can use a dispersion device. Now, this particular cartoon picture shows a prism, okay? But oftentimes you can use a grating, and oftentimes people do use a grating, a reflection grating like we talked about before last video. But whatever you use separates the light into the different colors of the rainbow, and you can really see that here, okay? We've got the Roy-G pattern at the top left, where that light is projected onto that so-called photodiode array. Again, this photodiode array is a series of a large number, hundreds, if not 1,000 or more, individual photodiodes, which are individually addressable light detector. Each and every one of them is. And I can measure the intensity at each and every photodiode independently. And the cool thing about that is each photodiode gets a very specific wavelength range that it's responsible for, usually a narrow wavelength range, maybe a nanometer or two, something like that, okay? But each photodiode is responsible for that very specific wavelength. And that's cool because the photodiodes, they only require millisecond time frames to make a measurement. They're very, very quick. There's no need or desire to move parts here at all. We don't need to scan our prism or grating, just keep it all fixed and stationary. Nothing needs to move. And that means that it requires a very, very short period of time to acquire a complete spectrum because all those sensors, all those photodiodes are working at the same time to measure their own specific wavelength region. So to make a measurement, what you would do is the cuvette where it's a sample, you'd have to make a blank measurement first with your solvent that basically contains everything except your light absorbing compound. So you'd make that as a blank, okay? And in the computer that runs this scheme, you would set that as your 100% transmittance for all wavelengths. So your photodiodes would see what it looks like to have 100% transmittance or the full brightness, right? And then you would take the cuvette and you'd place your sample in it and you'd return that cuvette to the optical mount in the photodiode array spectrometer. You'd push a second button for a run. And then the light incident on the diode array would be a little less than what it was for the 100% transmittance. And at every single wavelength, you could do the transmittance calculation for what the percent transmittance is at every single photodiode in the array. And you would get, your transmittance as a function of wavelength. You can convert that to absorbance. And in a matter of milliseconds, you can get a complete absorption spectrum throughout the UV visible and even into the near IR. So these devices, because they don't have moving parts, because they can get extremely rapid spectra, are really kind of taking over the predominant design for UV vis molecular absorption instruments. All right, and with that said, I think I'm gonna quit the video here. And we got one or two more for this chapter, and then we will be done.